Okay, so here's where we were last time. We were talking about Green's theorem, and we actually just kind of barely finished writing down the theorem. So here it is, Green's theorem. This is the way I like to write it anyway. There's different ways to write the theorem. There's different notations to represent the two different sides. What I have written as Green F here, that's just my notation for what I like to call Green's operator, but dq dx minus dp dy. Really, this is the more common way to write it, so certainly you're going to see that a lot. I just like having something compact. Also, I think this is an important operator, and important things deserve names, so this makes sense. Anyway, likewise, we talked about how this integral is sometimes written in coordinate notation, right? And pros and cons. In Math 212, mostly cons. But nevertheless, in a lot of contexts, this is how you will see the left side of Green's theorem written very routinely. So heads up, you'll certainly see it that way a lot. I would suggest that this is the way you think about Green's theorem. Specifically, think about the object that's being considered is this thing. This has we've previously discussed sort of natural interpretation with respect to fluids, namely that if this represents how fluids are flowing, then this vector line integral represents how much the fluid is flowing along the curve. If that curve is a boundary, then that says how much is the fluid kind of going around the boundary of this region D. It's in the same way that the boundary itself is. In other words, it represents how much the fluid is, as we like to say, circulating. Right. So I think it's more sort of clear to make this connection here with this notation. But anyway, so certainly either way you see the algebra, don't forget what the left side is computing is circulation of a fluid. That's the way you could think about it anyway. And then likewise, what is this thing? Well, it's that's what you do to a vector field to identify, in some sense, the density of this circulation. So, grand total over the entire solid region, there's a certain amount of boundary from y'all's point of view, a certain amount of boundary circulation, right? How much of that boundary circulation is happening near any given particular point? So, in the same way that you can think of the derivative as change density, weird of a perspective though that is, it's pretty natural, pretty meaningful. Likewise, Green's operator is circulation density. Okay. All right. All of this said, one handy thing that you can do with Green's theorem is you can connect two algebraic objects, one of which maybe you need to compute, the other of which is easier to compute. And that's awful handy, right? So specifically, very often what we're going to find is that we find ourselves looking at a vector line integral that, may be hard to compute. But maybe this double integral is easy to compute. So that's a lot of the applications come in this form, but I also think it's important to understand sort of, geometrically, physically, how do you visualize it. Okay, so we did an application last time of how to compute a line integral. We rewrote the line integral as a double integral of Green's operator, just like the previous theorem says. Now, very quick observation. Notice that when you go this way with it, when you say, I've got this line integral I want to compute. I can rewrite it as a double integral. That only works when your line integral fits this form. Notice this line integral, very importantly, as we've discussed earlier, this is a line integral over a boundary curve. That is a critical requirement if you want to use Green's theorem. Green's theorem only addresses line integrals around boundary curves. If you just have some random curve like that, Green's theorem does not comment on that line integral. That's not a boundary. Okay, so this example here worked because we were looking specifically, you can see right there, at a boundary of a two-dimensional region. And we won't go through the details again. We went through this all last time. But that curve, you can see, is a boundary, and it's a boundary of that disk. Okay. All right. So another example. Let's consider this line integral. This line integral around a certain curve, as drawn below, and here it is. So kind of a sort of a triangular figure 8, if you will. Right? So I'm going to compute a line integral along that curve. I've got a vector field given. Now, let me just remind you, there's different approaches that you could take. One thing you could do is you could brute force this. You can parameterize. Here's the problem with parameterizing. Obviously, this curve is made up of 4 pieces. So there's that piece, there's that piece, there's that piece, and there's that piece. And so you'd have 4 separate parameterizations to make. It's not that you can't do that. You totally can. It's just going to be inconvenient. So again, plan B, right? Let's not lead with that as an option. What we're going to do now is try to figure out if I can use Green's theorem. Can I think of this curve as being a boundary of something? And there's a temptation to say, yeah, I mean, look at our curve. Here it is. And there's a temptation to say, oh, yeah, check it out. It's the boundary of, well, what's inside the figure 8. Right? Tempting. Here's the problem. It doesn't really quite work. So here's the problem. There's our first little triangle over here. Let's look at its boundary. The boundary of that little triangle is that piece of curve going that direction. Oh, good. It's going the right direction. Boundary continues. It's that piece of curve going that direction. Again, also, that's the direction of our curve C. That's the direction we're supposed to be going. And then likewise, that piece of curve with that direction, again, going the direction we want. Looking good so far. Boundary of D1 is kind of, if you will, the left half of the curve that we're interested in. The problem is that if you look at this right side triangle and talk about its boundary, and again, I emphasize, when you say the word boundary, boundary means a certain thing. It means it's the curve, but it's also with a prescribed orientation. Boundary does not mean look at the edge and then go whichever way is convenient for your purposes, right? Green's theorem was written down with a specific convention in mind. So the boundary of D2, it's that edge going that way, which is the wrong direction. Here, let me do this in red because it's wrong. That's edge going that way, which is the wrong direction. That's not the direction C goes. If I say boundary of D2, I get the correct edge going the wrong way. I get this edge. That's how boundaries go. Again, going the wrong way. And I get that edge. Again, that's how boundaries go. Again, going the wrong way. Okay, so that's bad news. So it'd be a mistake to say that our curve C is just the boundary of D1 and D2 sort of naively together. Here's the good news. The good news is that exactly wrong is actually not 100% bad. Right? We have here something that is not what we're looking for. It's exactly opposite of what we're looking for. It is therefore the negative of what we're looking for. Right? So if I talk about the boundary of D2 going around this in the way that boundaries go, I get the exact negative of what I'm interested in. Keep in mind what I'm interested in is the curve C as it's described, which goes around the other way. So all we have to do to fix that which is exactly wrong to become exactly right is throw a minus sign in there. So this is a surprisingly common occurrence. So heads up, be on the lookout for this kind of thing. So instead of rewriting C as, just D1 and D2, just realize you have to subtract the boundary of D2 line integral to be going the correct direction. That said, we have here now a couple of line integrals around boundaries. Line integrals around boundaries are what Green's theorem computes for us. Green's operator is easy to compute here. You take this vector field and plug it into Green's operator and, dq dx minus dp dy, easy calculation. Obviously, I've arranged this example to work out nicely. Integrand is 1. And so what I get is this area minus this area. Clearly, those areas are the same. Oh, I'm sorry. Details. I should have labeled at the beginning that these edges are here 1 and this is 1, 1. So these are identical triangles, and the areas are the same, and the difference is 0. And easy calculation. Yeah. Yes.
What happens if only one of the edges is going in the wrong direction?
Then you can't do this trick. Yeah, and here's the good news. Stuff works out nicely far more often than it does not work out nicely. And there's a long discussion as to why that is, but you're quite right. I mean, if not all the edges lined up, then it would not be the exact negative of what we're looking for, and this would not work. Yep. I don't want to say you'd have to parameterize, but this method would not work. There might be conceivably be some other clever approach depending on the situation, but it would depend on those details that we don't have. Yeah. Okay. So there's that example. I want to show you another corollary of Green's theorem. I think this is really nice. Here's Green's theorem again, by the way. Straight up Green's theorem. Now I'm going to apply Green's theorem to a very particular, carefully chosen vector field. That one, 0, x. I'm choosing this particular vector field because of how nicely things will work out if I do, right? I don't have to do this. This is a choice, right? So first the observation that having made this choice, the vector line integral, you can rewrite it in coordinate notation like that. Don't forget, integral f dot dx is integral p dx plus q dy. So that's all I'm doing there. This is just that coordinate notation. Then also, let's take that vector field and plug it into there. What is Green's operator there? Well, dq dx minus dp dy, the usual formula, and as it turns out, that's 1. We have here a double integral of 1. Double integral of 1 over a region gives you area. So here's the nice punchline. You piece all these pieces together, and what it tells you is, nice general fact. This one single coordinate line integral here, boundary line integral of x dy, that little special little coordinate line integral, going around the boundary will compute the area inside. It's weird, but it works. Okay. And there's a geometric point of view you can take, but we don't have time to talk about that. Now, you might say to yourself, thanks, but no thanks, I'll just compute area by previously existing techniques. I wouldn't prefer to do a coordinate line integral. Okay, sometimes it remains, though, that's still easier. This is still a good trick. But sometimes this coordinate line integral is really easy to compute. Here's the special case I want to talk about. If you are looking at a line segment from some starting point to some ending point, this coordinate line integral over that line segment is computed by a super easy formula. Average value of x times change in y. It's 3-function arithmetic. 4. Excuse me. You have to divide by 2 to compute an average, I guess. So 4-function arithmetic, just barely. Okay. So really easy. Now, to be fair, this line integral has to be around a boundary. Line segments can't be boundaries, right? But boundaries can be made up of line segments. So, for example, if you find yourself in this situation here where you're looking at this odd polygon, weird little polygon, you want to compute the area of that, you've got a weird little geometry problem in front of you here. Think about it, right? The angles that we're looking at are not right angles. There's a bunch of weird, wacky little angles. So, I guess you could think in terms of, breaking it up into triangles, but then how do you compute the area of each one of these triangles? This is not a trivial problem, but I can say, for the corollary of Green's theorem from the previous page, that area is line integral around the boundary of x dy. I can break that up into little pieces. Right? On each little piece, we're looking at a line segment, and therefore, simple arithmetic. So let's look at that third line segment, for example. All the others are morally equivalent. On that third line segment, I'm going from, well, let's see here, what is the average value of x on that line segment? Well, let's see, it starts at x equals 3, it ends at x equals 4. The average of that is 7 halves. Super easy arithmetic. Okay. What is the change in y? The change in y, well, this y coordinate minus that y coordinate is, it gives me my delta y, and that's, again, super easily computed as 4. Do note the direction matters. So it's 4 minus 0, not 0 minus 4. It's endpoint minus starting point to make sure to go in the appropriate direction. And that arithmetic is crazy simple. So likewise on all the other pieces, take this edge here, for example, average value of x. Well, let's see, from negative 1 to 3, the average value of x is 1. The change in y, well, y decreases from 4 to 3. So delta y is negative 1. Again, crazy simple arithmetic. There you go, and there's that area, that otherwise seemingly nasty geometry problem. Which, yes, you could take a clever approach and compute this in a certain clever way, but arguably this is also pretty darn clever. Yes.
You can do this only when the integral is x dy.
Well, x dy is the tool that we're using. So we showed back here that if you're interested in computing area, note this problem did not come at us as compute integral x dy. It came at us as how do you compute this area? And then we chose to make the connection that, per this example here, that area is integral x dy. Now, there are other vector fields that you could put here that would give you different, you get something different over here. And you could do that too, but I think this is the easiest one, so I would encourage you just to do this one. Yeah. Okay. So, several examples under our belt now. I want to go back and talk about some kind of abstractions. There's some really powerful ideas that connect Green's theorem to previous stuff that we've done. And let me just remind you, we talked about the fundamental thermal line integrals. The fundamental thermal line integrals connects line integrals to just plugging into some magic anti-gradient function, right? And when you're doing line integrals, you're talking about stuff like path independence and that kind of thing. Right. Okay. Green's theorem is seemingly in a totally different context. Green's theorem is talking about areas and double integrals and stuff like that, but also line integrals. So both fundamental thermal line integrals and Green's theorem cover kind of the same turf, right? And let me go back to the several pages back where we have our diagrams written. Let me just remind you, where did I thought these were, here we go. These diagrams are just for kind of bookkeeping purposes to help you organize the ideas in your mind. I guess while we're here, let me go ahead and observe that fundamental thermal line integrals says if you take a boundary of a curve and the gradient of a function, then that evaluation and that evaluation are equal. Now notice Green's theorem, I guess we mentioned this last time, but Green's theorem says if you take a boundary of a region, which is a curve, and if you take Green's operator of a vector field, the line integral of that vector field over the boundary curve is the double integral of the Green function over the given original region. Right, so structurally, these two theorems fit on the diagram highly analogously. Here's another thing, though. Let me remind you, we did already talk about, I didn't really address this notation down here, but we already know that Green's operator and the gradient operator connect to each other, but I haven't given you any sort of point of view on why that ought to be. But reminder, if you look at a gradient, then when you compute Green's operator, you get 0. And also, if you have a vector field for which Green's operator is equal to 0, then that vector field is a gradient. Very important asterisk. Don't forget, this stuff only works if everything in sight is well-defined and continuous and differentiable everywhere, and I mean everywhere, and if there is so much as one point in the domain where this isn't true, then all bets are off, right? So that's very important, little asterisk. One of the homework questions kind of shows an example of how badly things can go wrong if that regularity isn't satisfied. But anyway, assuming regularity, Green's operator and the gradient operator kind of fit together. So I've asserted, completely without context, and now I'd like to give you some sort of point of view on why, morally speaking, that kind of not only is true, but why it kind of ought to be true. So how do you think about it? And here it is. I think this is a really nice calculation, or little observation. Here we go. So let's suppose you have a couple of points given. And I'm going to think of this as the first point, and I'm going to think of that as the ending, sort of the second point. So starting point, ending point. With those having been given, let's think about a couple of curves that start and end at that point. Here are those two different curves. And notice, I've got this drawn. Those two curves then bound a two-dimensional region. Or you could say this differently. You could start with any two-dimensional region, right? Pick a couple of points on its boundary, and then draw these two curves, C1 and C2. Okay. So with this arrangement having been set up, note first that the boundary of C1 and the boundary of C2 are equal. Right? Both of those boundaries are, they start at point 1 and they end at point 2. So C1 and C2 have the exact same boundaries. Now, awkwardly, let's think about D then. The boundary of D is, let's think about it. I claim it's C1 minus C2, and here's why. That boundary of D, keep in mind the rules for the boundary of D are you go sort of around the outside, right, but with such a way that the region is on your left. And notice that means we're following C1 in the direction that C1's going. And then we are following C2, but opposite the direction that C2 is going. Thus, the minus sign. Yeah? Okay. All right. Okay, so there's our setup. What's one of the weird things about this particular situation, it leads to some language problems in terms of talking about these orientations on C1 and C2. And let's ask the question, just for rhetorical purposes, are C1 and C2 oriented the same way, or are C1 and C2 oriented opposite ways? And from this point of view, they start at the same point, they end at the same point. Kind of tempting to say they're oriented the same way. Everybody see that sort of temptation? They start and end at the same place. Seems like they're going the same direction. But from this point of view, it's kind of like they're going opposite in the sense that C1's going counterclockwise, C2 is going clockwise. Those are not the same, those are opposites. So, which is it? Are they going the same direction or are they going opposite directions? The reason I bring this up, again, it's for rhetorical purposes. The correct answer to the question is that C1 and C2 are going in directions that can't reasonably be compared. They're different curves. You can't compare the orientation on this curve with the orientation on that curve. They're different curves. Are these two purple curves going the same way or opposite ways? It's a ridiculous question. They're different curves. Right? So don't fall into the trap. It's a common conceptual trap to try to compare whether these are same or opposite. They're neither. They're different curves. You can't compare them. You can't compare their orientations at all. All you can do is talk about how they have the same boundary. Yes, absolutely. As part of the boundary of D, they are going opposite. They have different. They make opposite contributions to the boundary of D. If you want to say it like that, right? Their orientations themselves are not comparable. Okay. All right, so why do we set this up? I'm just going to write down Green's theorem. Here it is. Green's theorem says the double integral of Green's operator over the interior is equal to the line integral around the boundary. Don't forget that boundary is C1 minus C2. Right, so there's Green's theorem. So all it is Green's theorem applied to this picture, observing what we've observed. And it turns out this equation is very, very nicely set up to let us do some nice things. Let's consider a hypothetical scenario. Let's suppose that Green's operator is equal to 0 for some vector field, whatever, just some vector field. If Green's operator is 0, by which I mean if it's always 0. Right? If it's flat 0. Well, then that integrand is 0 everywhere. That means this double integral is 0 everywhere. Well, if this is 0, that means that difference on the other side of the equation is 0. Wait a second. If a difference is 0, that means that the two separate line integrals here, making up the difference, must be the same. These two line integrals are the same. These two line integrals of f along curves C1 and C2 that start and end at the same point are the same. And this is true for any picture you draw. This is true no matter what starting point, no matter what ending point, no matter how you draw these curves. That means that this vector field is path independent. And we saw previously that vector field that's path independent is a gradient. And so this gets us to, why that lifetime, there's a geometric perspective anyway on why that theorem is true. Green's operator is 0, that's a gradient. Morally speaking, this is why, intuitively speaking, I'll say this is why that is. Because of this picture. Very loosely speaking, details aside, an alternative way of viewing that is you can look at this picture and say, well, this is kind of a picture of Green's theorem, because look, it's a region with a boundary. But you can also look at this picture and say, hey, this is a picture of path independence, because this is a picture of two curves starting and ending at the same point. And this happens to be that this picture is actually arguably a picture of both. And that's kind of neat. Everybody happy with that? Any questions? It's a neat argument. Okay. Likewise, going the other way, what if you have a gradient? Let's look up here. If we have a gradient, here we go. Gradients, we know are path independent, again, from previous discussion. Path independent means that these two integrals that over curves that start and end at the same point will always be the same, and therefore this difference is 0. Well, if that difference is 0, that means this integral is 0, and if that integral is 0, now wait a second, that integral is 0, no matter what picture I draw, no matter what region I pick, what function could possibly be in here? What could this possibly be? Whose double integral is always 0 on every domain? Only the 0 function. Right? So this sort of argues sort of the other way around. If you have a gradient, then Green's operator is equal to 0. So this is, like I say, it's a geometric perspective on. Whoa, I'm hitting the wrong button. Sorry about that. Let me go back over here. That's what I meant to do. Sort of a geometric perspective on these lifetime theorems down here. Everything has a lifetime of 2. Green's operator is 0 means that you have an anti-gradient. We have a geometric point of view on that now. Okay. All right. Okay. All right. Here's another application. By the way, this application serves several roles. It's a nice application of Green's theorem. Also, this is a good segue into our next topic. We'll get to in a few minutes, time permitting. Oh, yeah, we're doing good. And this is also a first point of view on a topic that we're going to touch on later in the class when we get to Gauss's divergence theorem. So that's very distant foreshadowing. So we're going to have multiple perspectives on this. So anyway, here we go. here's what we're going to consider. We're going to consider what do we mean by something called flux through a curve. This word flux you've probably not seen before. Flux says we've got a vector field. Vector fields could represent lots of different things. In this context, let's pretend like our vector field represents flow of a fluid. Now you remember, start of chapter 15, I made the observation. Sometimes vector fields represent flows of fluids. Sometimes vector fields represent forces, like gravitational fields or something like that. And these are very different physical metaphors for what a vector field might represent. You have to be able to think about vector fields from both of those points of view. Here, we have to think of this vector field as representing the flow of a fluid. If you're stuck on thinking of vector fields as representing things like gravity, that's not good. We definitely need to be able to think of this as representing the flow of a fluid. Okay, so we have a fluid flow. You can imagine some fluid kind of flowing along the page there. And then we also have that piece of curve. And here's a pretty reasonable question you could ask. This fluid's flowing along, and there's that piece of curve there. Hey, how much of that fluid is flowing across that line per unit time? Right? Quantity per unit time of fluid. Notice that's not what the vector field itself tells you. The vector field is telling you the velocity of the fluid at any given point. It's got units of distance per unit time. Right? We're asking for volume per unit or area per unit time. You know, how much quantity of this fluid is flowing over that curve. And this is a stickier question because notice how much it depends on orientation. So, for example, if you have, let's suppose your vector field is like this, just to make an easy one. Right, there's that vector field. Through that piece of curve, there's a lot of flux. There's a lot of fluid flowing across that line. Across that line, there's hardly any fluid flowing across that line. There's a lot of fluid flowing near that line, but not across it. Everybody see what we're talking about here? Okay. So one way to think about this, if you want a physical metaphor, I like to think of fishing nets. Right? Now this is two-dimensional, not three-dimensional. We'll do the three-dimensional soon, but nevertheless, you can sort of see the analogy. If the curve here were representing a net, and if the fluid flow represent water flowing through the net, and if we think of fish as kind of being stuck in the water, right, and they go where the water flow pushes them. This is not a good way to catch fish. Right? The fish inside of this fluid, there's a little fish, and he just flows right on by. And he's like, hey, look at that weird thing down there, right? And you don't catch that fish because he didn't flow over the curve. He didn't flow over the net. Right? You do it the other way, and of course, you catch the fish there. Okay. All right. So, very natural thing to want to talk about. There's an easy way to justify a formula for this, and that is, per the last example we just mentioned, I don't really care about how much the fluid is flowing along the curve. Just don't care. That's not relevant, as it were, to what we're looking at. We're looking at, for this vector field, to what extent is that fluid flowing perpendicular to the curve in what we call the normal direction. Y'all remember little n for normal vector. So to what extent is the fluid flowing along the curve? The extent to which the fluid is flowing along the curve, the more the fluid is flowing, perpendicular, the more the fluid is flowing through the curve, more fish are going to catch. The more flow there is over that curve. But, of course, another thing, bigger nets catch more fish. Yeah? Okay. So, with this picture in mind, this is what we're going to call flux. By the way, there's units to consider here. I don't want to worry about the units. Maybe you're interested in, area or, geometric quantity of fluid per unit time. Maybe you're interested in mass and the density is not constant. These are little details that you can work out in other contexts. But big picture, we're going to think of flux as being, again, quantity of fluid per unit time, and it's computed by this formula. It's just the n component of the vector field times the size of the piece of curve ds. Reminder, components are computed with dot products. Chapter 12, old news. How are we doing? Is everybody on board? Okay. So here's a situation. Then I just skipped over some stuff. I'm going to come back to. Suppose I have not just a single piece of curve, but suppose I have a region like this with a boundary curve like that, and maybe this fluid flow represents some quantity I'm interested in. Look, it could be surface water on the map, right? Or maybe it's a migration pattern of birds or wildebeests or whatever, right? So we got some fluid, some flow represented by this vector field, and it's a pretty plausible thing to want to know the grand total of all of these fluxes. If you think about it, if you look at the flux through that piece, plus the flux through that piece, plus the flux through that piece, etc., if you go all the way around the entire boundary, you're looking at all of the exit of fluid, all of the entrance of fluid, all together. And that tells you how much of this fluid total is flowing into or out of this region. And that's a pretty darn interesting thing to keep track of, right? If you're trying to keep track of birds in your, bird sanctuary or whatever they call them, knowing how many birds are flying out, how many birds are flying in is a good way to keep track of grand total. How many birds are in our sanctuary? Is everybody on board? Does it seem plausible? Okay. So, adding up over all these little pieces, over each little piece I can talk about how much flux. On each little piece, F dot n ds, per the formula on the previous page. Right? And so adding up over the entire boundary curve gives you that integral there. And so the question that is before us now, in order to compute flux, how would I compute this integral? Integral f dot n ds. And it looks kind of familiar, vaguely familiar, doesn't it? We've seen integral over a curve of f dot something ds. Bad news, that something is not what it's supposed to be. This, if that were t, then we know how to compute that. That becomes a regular old line integral if that were t, but it isn't. Very importantly, that's n. That's this normal vector facing out of the region. Like that. And it's just not the same as t. Right? Going along the boundary, unit tangent vector. Like that. It's just not equal to t, so I can't say, line integral f dot t ds, and then refer back to all our old formulas. Just isn't. Okay. All right, so here's the good news. This is something that we can easily relate to t. And this is a calculation on the previous page. Here's our normal vector for a little piece of curve. Here's the corresponding t vector. Okay. We've been asked to compute f dot n. So suppose we have some vector field f. This dot product is f dot n. That's what we want. I want to compute that dot product. So the innocent observation I make here is that, okay, well, that's what I want, f dot n. I just don't like the n. But if I were to just rotate that whole picture, just like, I rotate, let's see, color choices. I rotate n pi over 2 counterclockwise to get to t, right? If I just rotate f pi over 2 counterclockwise. We know how to do that. That's an easy formula to rotate something counterclockwise. I get this other thing called f rot, the FR, whatever you want to call it. Easy formula though. Right here. Then doing that rotation like that. Oh, I'm sorry, wrong color. The integral, the dot product that I'm interested in, f dot n, exact same dot product as this rotated f dot t. Because the green picture, if you will, the orange picture, if you will, those magnitudes pair up the same. When you rotate something, it doesn't change the magnitude. It doesn't change the angle between them. Both of these vectors you rotated the same amount, 90 degrees. Right? So dot products are the same. And so what I have then is that where I have on the next page, where I have f dot n, I can just replace that instead with this rotated f dot t. And so that's what we do here. I'm going to take this f dot n, rewrite as rotated f dot t, and it's all downhill from here. Everything's worked out very nicely. Don't forget we have a formula for this rotated f, negative q comma p, right from the previous page. Our old friend TDS is the dx vector, so that's just kind of a notational kind of alternative. And notice what we have now is an integral that's very familiar. This is around the boundary curve, vector line integral. Green's theorem directly addresses that. Green's theorem says that vector line integral is this double integral of Green's operator. How are we doing? Do be careful with one thing. A lot of students make the mistake of just writing down dq dx minus dp dy. It's not right, of course. Let me just for sort of visual convenience, when you write down Green's operator of something that has two components, and instead of calling them P and Q, let me call them blue and yellow. Right, Green's operator says you're going to take the x partial of one and then subtract the y partial of the other. But specifically, and think about the formula dq dx minus dp dy, what that really means is you're taking the x partial of the second component minus the y partial of the first component. Right, and in this case, don't forget what our things are. Our first component is negative q. And our second component is p. Right, so that's why this Green's operator right here is that. Right? You got to be real careful when you when things kind of when the letters that we use to represent things get kind of put in an order that we're not typically kind of accustomed to. It's a dangerous little algebraic situation. So anyway, it ends up being dp dx plus dq dy, and there you go. So this formula here will compute flux for you. If you want to know how much grand total, how many of all the birds flying out of our sanctuary, of all the birds flying into our sanctuary, grand total, what's our grand total exit rate? Canceling the exits and the entrances. This double integral does it for you. Okay. Alrighty. So we're going to move on now and spend a little time talking about the next dimension up. What we just considered here was flux through a curve. So if you have a little piece of curve, you can talk about fluid flowing through the curve. Right? Quantity per unit time going across that curve. And I just make the observation that, same thing if you had a piece of surface. Quick reminder, I emphasize, we're talking about vector fields representing fluid flows. If you think about vector fields as representing forces, you're going to get lost. This is not going to make any sense. That's not the motivation, a reasonable motivation for this idea of flux. So abandon this point of view on force for this discussion. So anyway, everything else kind of goes through the same. We have this fluid flow. Let's say like that, right? And I can talk about a piece of area, a piece of surface in space now. And same story, if I would like to know how much fluid is flowing through this piece of surface, per unit time. So volume, total volume of fluid per unit time. It matters how the surface is oriented. Again, think about this ridiculous situation of, suppose you have an ocean current going, that way. So the flow is that way. If your net is like this, with the flow like that, then there's a lot of water flowing through your net. You've got a chance to catch some fish. If, however, you make the ridiculous blunder of, with that flow of water, turning your net like that, then you just get confused fish. Right? You don't actually catch any fish because practically none of the flow actually goes through that surface. It either goes right above it or right below it. So how that surface is oriented, the relationship between the surface's orientation and the flow's direction, that direction relationship is very, very important in figuring out how much fluid's actually flowing through there. So same argument, if this is the vector field, then that component, F dot n, is what is telling you what you really want to know about the fluid. Again, more area, more flux, more fluids flowing through an area. If there's more area, stands to reason, right? So plausible formula is this flux that we're interested in is F dot n times area. How are we doing? That's three-dimensional version of what we did on the other page. Okay, now there is a flaw with this argument. Well, there's a shortcoming with this argument, I'll say. We're assuming that the vector field is constant, that the vector field is the same over there as it is there. What if that's wildly inaccurate? What if perhaps the vector field were changing dramatically at different points on the surface? What do you take the component of? Right, this doesn't make any sense at all. What if our surface is not flat? The nice thing about a flat surface is that at every point on this flat surface, that normal vector, exactly the same everywhere. Right? And so in which direction do you look at the component of the fluid flow? With what unit vector do you dot your fluid flow? Well, if it's flat, you've got a pretty good answer to that question. If the surface, though, is not flat, if your surface is curved, let's say like that, right, then your normal vector is very different at different points. So if this is our usual circumstance, right, we find ourselves in this circumstance a lot where, hey, we're trying to add things up in a context where the things we're adding are not constants. So we chop it up, add it up. It's the same story we've seen a million times. Here's the picture. Here's my curved surface. The normal vector is very different there compared to what it is there. The fluid vector is maybe very different there and maybe very different over here. Okay? It could be something like that, maybe. Chop it up into little pieces, though. On each little piece, the idea is that the fluid flow is probably approximately constant on that little piece, and the normal vector is approximately the same everywhere on that little piece. On that little piece, then, we have an easy question. d phi on that little piece, just this formula from the previous page, F dot n times area. And that simplifies very nicely in this context. If we're looking at a little piece, if on this little piece, if the area is ds, as was our choice of notation when we were looking at surface integrals a while back, then this just becomes a double integral f dot n ds. So there's our new kind of integral that we want to be able to compute. I've lost count. Let's count integrals again. So again, this is not one of our old ones. We've seen single variable integrals, double integrals, triple integrals, a bunch of computational techniques that weren't actually different. Let's see, we've seen scalar line integrals, but then vector line integrals. Those were different. Then we saw, maybe I got these chronologically out of order, scalar surface integrals. How much mass is there on a surface? What's the area of a given surface? How many ants are crawling on a surface? Scalar quantities like that. And this now then is our 7th new kind of integral. This integral represents not a scalar quantity of, how much of a scalar thing like mass is there on a surface, but how much of a vector quantity, a fluid that's flowing through the surface and therefore depends on orientation. So this is our 7th different kind of integral. Right, we're making a lot of progress in this class. But do keep in mind all of these integrals have the same underlying common strategy. Chop it up, add it up. Right? A problem is hard over a large region. If you chop it up into little pieces, on each little piece, the problem becomes easier, and you just have to learn how to add things up. And the details are different. We'll get to the details next time, but this makes for a good stopping point for today. See y'all later.